discussing subatomic particles and their relationship on the periodic table. Just as a quick review, here are the three different subatomic particles we'll be discussing: protons, electrons, and neutrons. Notice the mass of the protons and the mass of the neutron is very similar, while the mass of the electron is much smaller. We then relate these with the atomic mass unit, just so that way we have easier numbers to be working with, which is all based off of carbon-12. Notice the mass of the electron is much smaller. The protons and neutrons are found in the nucleus, where the electrons are roaming around outside. Protons have a positive 1 charge, while electrons have a negative 1 charge, and neutrons have no charge at all. And then finally, let's not forget about our symbols, because they'll be used quite often. Okay, atoms versus elements. When you read the definitions, they sound almost the same thing. But I like to think of it as looking at blocks. If you put all the green blocks together, and all the red blocks together, and all the yellow blocks together, and so on and so forth, you'll have all the colors together, but you'll find variations amongst the colors. For instance, with this yellow block, you have 4 dots, while this yellow block, you have 8. And this one over here might only have 4 or 6. Well, all the groupings are considered the element, and all the individual atoms make up the element, because they all have similarities. They all have the same color, like they all have the same number of protons with atoms. However, there's slight variations. For instance, isotopes will have different weights, and the elements, even though they have these variations, they still have the same number of protons to correspond with it. So the atoms make up the elements, are grouped as elements. So let's take a closer look at the elements themselves. They all have a very unique number of protons, and that's the atomic number. For instance, here for boron is 5, for carbon is 6. This is the atomic number. This also tells you the number of protons. So every carbon atom that's there will always have 6 protons. Every boron atom will always have 5 protons. And that's how they're arranged on the periodic table. Notice left to right, 5, 6, 7, 8. You'll also notice that each one of them have their own symbol. Some of them are extremely obvious, like oxygen is O, fluorine is F. Some of them have 2 letters. Pay attention to the fact that if it's 2 letters, the first one's always capital, the second one is always lowercase. Some symbols are not quite as obvious. For instance, iron is Fe, copper is Cu. That's because comes from their original names or Greek or Latin derivatives. I mentioned the word isotopes earlier. They're the same element, meaning that they have the same number of protons. So if we look at carbon-12 versus carbon-14, both carbons have 6 protons. It's this top number here that's changing, and that's identifying the isotope. They have a different number of neutrons, which is why these numbers are different. This one has 6 neutrons, and this one has 8 neutrons. And as a result, they have different masses. So carbon-12 has a mass of 12, carbon-14 has a mass of 14. But they react identically. So the mass number, which is that top number that I was playing with, are the protons and neutrons added together. I've been writing the symbol for quite some time now. I did that 2 or 3 times already. So X here is the atomic symbol. Those are the letters on the periodic table. The top number is the protons and neutrons added together. while the bottom number is the atomic number, which is just the protons. Which means if you were just looking for the neutrons, you would take the top number and subtract the bottom number. Because when you're doing that, you're taking the mass number and you're subtracting the atomic number. Which is the same thing as taking the mass number and subtracting the protons. So let's practice writing these atomic symbols. So boron's atomic symbol, we take the letter. It has 5 protons. That number goes on bottom. If it has 6 neutrons, you're going to add this number to the bottom number. So 5 plus 6 is 11. And that's where we get that number from. Lead has a symbol of Pb. Its atomic number is 82. The number of neutrons is 124, which brings it to 206. Notice in both cases, the top number is close to the atomic mass, but it's not exact. When we're talking about atomic symbols like this, we're talking about specific isotopes of that element. Whereas this number down here is the average of the isotopes. So let's take a second to practice these. Alright, so we mentioned that the atomic number and the number of protons are going to be the same. So if I have 11 for the atomic number, that means I'm going to have 11 for the protons. Same with this one. Same with this one down here. And same with this one. They're all neutral, so that means the protons need to equal the electrons, only because of the fact that they're neutral. We haven't talked about whether or not they have charges yet. So that means protons is the same as the electrons. So that means this is 11, that would be 31, that would be 29, and that would be 43. And this 39 will go back over here. So, atomic number, protons, and electrons are the same thing. Now the mass number, let's take a look at that one. That's going to be the protons and the neutrons added together. So the very first one we already have. The second one, we need to add 31 plus 37, because we have the protons are 31 and the neutrons are 37. So that means this number is going to be 68. We have the next one. And so here, the protons and the neutrons. The protons are 29 and the neutrons are 35. That added together will be 64. Now finally, we can figure out the neutrons by saying the mass number minus the protons. So this is going to be 24 minus 11, which comes out to be 13. This one's going to be 89 minus 39, because our mass number is 89, our number of protons is 39, so that comes out to be 50. And finally, the very last one, 100 minus 43, because this is our number of protons, comes out to be 57. The very last thing we need to do is figure out the symbol, and this is where we're going to look on the periodic table. So, we're looking for atomic number 11. Go to the periodic table, we find atomic number 11 is an A. The atomic number goes on bottom, the mass number goes on top. Do the same thing here for 31. 31 is gallium. That's Ga. 31. Then the mass number is 68. It's right here. The next one is 39. 39 is yttrium. It's right here. Atomic symbol is Y. Atomic number is 39. The mass number is 89. The next one is 29. 29 is copper. That's Cu. Atomic number is 29. The mass number is 64. The last one is 43, which is technetium. Number 43, and mass number of 100. So what about when the protons and the electrons are not the same? That's when we form ions. When compounds are formed, electrons are shared or given away and taken. Atoms that have lost or gained electrons are called ions. Protons always remain the same. It's the electrons that are affecting the charge. Electrons are negatively charged, so therefore if you lose electrons, you're losing a negative, which then become positive. Same with anions. We're gaining electrons, so we're gaining a -1, and they're becoming negative in that process. So lose electrons becomes positive, gain electrons, it becomes negative. Cations and anions. Ions behave much differently than a neutral atom. For example, the metal sodium, made of neutral sodium atoms, is highly reactive and quite unstable. However, the sodium cations, Na+, found in table salt, are very non-reactive and very stable. Since materials like table salt are neutral, there must be equal amounts of charge from the cations and the anions in them. Nonmetals typically form anions, meaning that they usually become negative. For each negative charge, the ion has one more electron than the neutral atom. For instance, fluorine, neutral, has 9 protons and 9 electrons. If we add an electron, we now have 9 protons and 10 electrons. That's giving us a -1 charge. Phosphorus is neutral at 15 protons and 15 electrons. When it has a -3 charge, it has 15 protons and 18 electrons. Notice the number of protons did not change in either scenario. It's the number of electrons that changed. Metals, however, form cations, meaning they become positive. For each positive charge, the ion has one less electron. It lost 1 electron. So, originally sodium has 11 protons and 11 electrons. When it's a +1 charge, notice it has 11 protons still, but now it only has 10 electrons. Cations, the calcium atom, usually have 20 and 20. The 20 protons remain the same, but in a +2 ion, it has 18 electrons. We can put together a little formula if that would help. The charge is always going to equal the protons minus the electrons. For instance, here, for calcium, the charge is equal to 20 protons minus 18 electrons, which comes out to be a +2. Alright, so let's practice these now. Okay, for this one, once again, the atomic number and the protons are always the same. So 16 and 12. We don't know any of the other information. The ion charge is going to be the protons minus the electrons. So in this scenario, it's going to be 16 minus 18, which gives us a -2 charge. Here, we can figure out the number of electrons by saying the charge, once again, is equal to protons minus electrons, which means electrons must equal the protons minus the charge. So, we know we have 12 protons here, minus the charge, which is 2, which gives us 10 electrons. We don't have the protons on this set, or the atomic number. So down here, we can say the charge, once again, is equal to the protons minus the electrons. So a -1 is equal to x minus 36. That comes out to be 35. That also means the atomic number is 35. Finally, let's look at this Al. That gives us a +3 charge right there. We can look on the periodic table to find Al. It's right here. It's number 13. That tells us that the atomic number and the number of protons are 13. We can figure out the number of electrons by simply saying the electrons are equal to 13 minus 3. That gives us 10 electrons. Now let's fill in the symbols. We are looking for atomic number 16 first. It's sulfur. And because of this, it's going to have 2 minus. You always put the number before the symbol, before the charge. The next one is atomic number 12, which is Mg. It has a +2 charge. And then finally, we're looking for number 35, which is bromine. And it has a charge of -1. There's other ways in which the periodic table is organized. Mendeleev was the very first one to organize the periodic table by how the chemicals react. He first arranged them by the atomic number, and then he was looking at the properties amongst those elements, and he came up with the periodic law. When the elements are arranged in order of increasing atomic mass, certain sets of properties recur periodically. He put the elements with similar properties in the same column. So this is Mendeleev's original periodic table, and this is our modern periodic table. We can find similarities. For instance, if we take this row right here, boron, B, C, N, O, and F, we can actually find that organization right here, B, C, N, O, and F. If we look at B, E, and Mg, they're right next to each other. They're right next to each other right here. Li and Na, once again, right here. So if we actually turn this to the side, you can see a lot of similarities between the two, which is why he's the one who's credited for creating the modern periodic table. He used patterns to predict the properties of undiscovered elements as well. And if we look at T, E, and I, look at the masses that are leading up to it. 114, 118, 121, 127, 126. It actually goes up and comes back down. That's because he allowed the properties, the chemical properties of the elements to dictate where the elements are placed. So he actually made adjustments like that. So that brings us to our modern periodic table. Alright, so the metals are all the blue ones. So the majority of the elements on the periodic table are indeed metals. With the exception of mercury, which is right here, metals are usually solid. They're shiny, they conduct both heat and electricity, they're malleable, which means they can be shaped, and ductile, which means they can be pulled into a wire. They lose electrons, forming cations. So these are all going to be positive when they react. They're 75% of the elements, and they're on the lower left of the table. Nonmetals, however, are the pink area up here. They're solid liquids and gases, and they're poor conductors of heat and electricity, meaning that they're insulators. The solids are typically brittle, and they gain electrons, meaning that they become negative. And then the upper right hand side of the periodic table. The one exception is actually hydrogen. He actually belongs over here in the nonmetals as well. They just placed him in the other area because they react more like lithium and sodium. And then the metalloids are in the yellow. And they have characteristics of both metals and nonmetals. They're also called semiconductors. So the elements with similar chemical and physical properties are in the same column, meaning they're up and down. These columns are called groups or families. They're designated by the number on top, so that's why you have a 3, 4, 5, 6 up here. The rows are the horizontal ones, going left to right. These are called periods. Each period shows a pattern of the properties repeated in the next period. The main groups are designated by a letter A, so these are up here, and the transition elements are designated by a B. And the transition elements are always metals. The bottom row, the ones that stick out at the bottom, are called intertransition metals, or rare earth elements, which are once again metals, and they really belong right in here. So here's another picture of it. So these are the rare earth metals down here. These are the yellow ones are the transitions. And a lot of times they'll put an A's up here, and B's are in the transition metals. I've also seen them designated just numbering one across 1 through 16. But A's and B's are more common. So let's talk about some important groups. Let's talk about hydrogen by itself. It's a nonmetal, it's colorless, and it's diatomic, which means that when it's found in nature, it's never just hydrogen. It's actually H2. That'll trick you sometimes, so you got to remember that. Very low melting point and very low density. Reacts with nonmetals to form molecular compounds such as HCl and H2O. Alkali metals are underneath the hydrogens. The hydrogens are usually placed here, though it doesn't really belong. They're soft with low melting points and low densities. And when you put them in a flame, lithium turns red, sodium turns yellow, and potassium turns violet. They're very active and never combined in nature. The alkali earth metals, supposed to be an E here, are harder, they have higher melting points, and denser than alkali metals. Magnesium alloys is often used as structural materials. When it's put under a flame, the calcium turns red, strontium turns red as well, barium turns yellow and green. They're reactive but not as but less so of the alkali metals. The halogens are right here. They're group 7A. They're nonmetals. F2, Cl2, Br2, and I2. F2 and Cl2 are gases. Br2 is liquid, and I2 is a solid. Notice all of them have the 2 next to it, just like the hydrogen did. That's because they're diatomic molecules. They're also very reactive. And finally, we have the noble gases. All of these are gases at room temperature with very low melting points and very low boiling points. They're very unreactive and practically inert. Inert is just another word for meaning unreactive. They're very hard to remove an electron out of or give an electron to. So let's talk about this movement of electrons in a little bit more detail, and let's talk about it in relation to the periodic table. The charge of an ion can often be determined from the element's position on the periodic table. It's really important that you learn how to use the periodic table, not just where things are. Metals always form positively charged cations. For many main group metals, the charge is equal to the group number. Nonmetals form negatively charged anions. So the very first row is going to be a +1. Second row is going to be a +2. Third row is going to be a +3. We're going to skip the fourth row, and it becomes -2, -3, -2, -1, and then because the noble gases don't really react real readily, that's going to be a 0. So you can actually determine what the charge is by looking at the periodic table. For instance, potassium, we know this is +1, +2, +3, -3, -2, -1. We can look at where it is and determine its charge. Potassium is right here, so it has a +1 charge. Sulfide is sulfur right here. It has a -2 charge. Calcium is right here. It has a +2 charge. Bromide is right here. It has a -1 charge. And aluminum is right here, and it has a +3 charge. That is your information on the different subatomic particles and how they're related to each other.